All right. Hello, everyone. Welcome back to Math 162, Week 8, Lecture 2. Not a lot of time left in this course. It's crazy how time flies. I know I've said it before, but I'll say it again. It always just seems to go by super quick. So just going to talk about our whiteboard that we can see here. Couple of, or most of these shouldn't be a surprise as they'd already been discussed previously. 7.1 and 7.2 due today, of course, because they were done a week ago. 7.6 due on the 20th as we finished it last class. That was our introduction to vectors. And then we will knock out 7.7 as well as 11.1 today. So those will be both be due in 1 week, which will put us on the 22nd for those due dates. Now, I want to let you know that the third test for us is going to cover chapters 7 and 11 because chapter 7's only 4 sections and it's a little shorter than chapter 6's four sections. And then chapter 11's only 3 sections, and again, arguably significantly shorter than chapter 6. So it just feels weird to do a test on these chapters individually or to split it up in some weird way. So I like to combine them. Sometimes I've combined chapter 7 and 10 for tests. Sometimes I've combined chapter 7 and 11 for tests. With my summer classes, I like to do it this way for a couple of different reasons. Chapter 11 is going to play a more important role when you get to calculus, Calc 1 and Calc 2 especially. Chapter 10 is an awesome section. It's all about conic sections. We will get into that material. We're just going to do it last because I don't want to say it doesn't play as an important role that sounded weird. I don't want to say it doesn't play an important role in your mathematical careers because it's really cool, it's really awesome stuff. But admittedly, in the sequence of courses you traditionally take in college, at least initially, your first couple semesters in calculus, differential equations, things like that, you don't really get into a lot of conic section stuff the way that we treat it in chapter 10 of this course. So it's going to be a cool, different perspective. Again, we will get through most of that ultimately. It just will feel a little rushed at the end, and I'd rather have that be the material we don't throw in a regular test by itself. I'm not saying you won't see it on the final, hint, wink, nudge, but yeah. So the third test will cover the 4 sections from chapter 7, all of which you can see right here, and then it'll cover the 3 sections from chapter 11, which are 1, 2, and 3, and that'll be our third test. You will be allowed a calculator. That date, I'm going to go ahead and let you know, is going to be the 26th and 27th, those dates. And then we'll talk about that more next time. You'll see it all written up officially. Also, verbal warning, the final exam is going to be Thursday, the 29th. We will not hold class that day. It is a one-day test only. And again, we'll talk about more details with that next time. But for now, let's pick up where we left off last time. Like I said, we finished 7.6. We got a nice introduction to vectors. We talked about, all the different stuff. I'm not going to reiterate in the interest of time. But in 7.7, we're going to continue with vectors, and we're going to talk about something known as the dot product that has some pretty cool implications. So let's go ahead and get into that. And I'm actually going to leave this up for about 15 seconds before I hit play because I started rambling a little too quick, I'd say.
The dot product and going right to the definition of what the dot product is. We call it a dot product because you're going to put a little dot between the two vectors implying multiplication. So this right here has to be a dot. We have that x is a multiplier, like 5x7 is the same thing as 5.7 for real numbers and for imaginary numbers. But for vectors, they're not the same thing. If this was a vector times another vector, this would not be the case. So please understand that these two different notations for multiplication mean very different things in the land of vectors. We have a dot product And then another thing that we do have, but we won't be talking about in this course, is the cross product. This symbol is used for a cross product of vectors. And again, it is something different. So a dot versus an x between your two vectors means something completely different. A dot product is just this right here is the product of the x components. And this right here is just the y components being multiplied. So this is also known as a sum product because you're going to multiply the x components, then you're going to add, you're going to multiply the y components. If we were doing this in 3 dimensions, then you would add and you would do the z components, the 3rd dimension components. So the vector u we're calling its x component a sub 1 because we got 2 vectors. So then vector v has x component being a sub 2. And then conversely, the y components are b1 and b2. Now you might say, well, Mr. Beckner, why do you need to call them u and v? Why not just call them v1 and v2? Actually, yeah, you can certainly do that. Instead of going u and v, you can say v1 is a1i plus b1j, and then v2 is a2i plus b2j. There's nothing wrong with that. There's nothing wrong with just going with the subnotation for the vector labels in addition to the component labels. But in our course, we're usually given a u, a v, maybe a w. There can be a 3rd vector, a w. And then if I wanted to do u dot w, it would just be take the w's x and y components instead of the v's. That's all. All right. So the dot product. Notice in the actual process, this is what we'll do. We'll multiply the x components, we'll multiply the y components, and then we add. In this, there are no i's or j's. The answer is a number. It's not a vector, it's a scalar. Let me be more specific. A number, scalar. Scalar, 2 a's. The answer to a dot product is just a number. It does not have direction. Now guess what? The cross product is. That's right, you guessed it. The answer to a cross product is not a scalar, it's a vector. So we have a way of multiplying vectors to get just a number, and we have a way of multiplying vectors to get a vector as an answer. But it involves matrices, it involves the determinant of a matrix, and we haven't taught you matrices yet. We definitely haven't taught you the determinant of it, so we're not really ready to do that, nor will we even do it in this course. So the answer to a dot product is just a scalar. It's just a number. There are no i's, there are no j's. See, the a's do not have the I or j in them. Same for the b's. It's just the scalar. So scalar, 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 scalar. So here's the little note I talked about, the cross product. And then the whole reason we even do this at all, because we're very often looking for 2 vectors to be orthogonal. An orthogonal means that they form a right angle. Erase all the stuff I have circled. 2 vectors being orthogonal means that they meet at right angles. So here could be your u vector, and here could be your v vector. But these are boring. These are pretty much just axes. And you could get, sorry, my mind just went blank for a second. You could get a unit vector in each of those directions, and because they're the x and y axes directions, the unit vectors would be I and j. Well, what if they don't start at 0 and 90 degrees? Maybe this is your u vector, and then this is your v vector. So I'm trying to illustrate that there is a 90-degree angle formed between them. So it just happens to be that if the dot product of 2 vectors is 0, then they form a right angle. They are orthogonal. Now you might say, why do we need another fancy word for right angle? Well, when we talk about right angles in 3 dimensions, it gets a little tougher to see visually because you're drawing on a piece of paper and your right angle may not be in the plane of your paper. And when you start talking about math in the 4th and 5th and 6th dimensions, you can't even really draw it up without your brain exploding. And if you can't draw it up, you're just going to have to be able to imagine this right angle formed thing somewhere. And we just go with a fancier name because 4, 5, 6 dimensions are much fancier. This is math with a top hat and a monocle on it, so to speak. So orthogonal means right angles. And a lot of cool things happen with orthogonal vectors. You can make what's known as an orthogonal system, which is really easy to just, instead of having your basis vectors go right and up, maybe they go at this particular angle right and up and this particular angle left and up. Maybe it's just that everything you're doing is always on this crooked axis, kind of like how our Earth is tilted on an axis. We're off by a few degrees. So maybe you would rather just do all your math in a world where, okay, your axes are slanted and this seems really goofy, but these vectors, you can make very, very, very nice unit vectors out of them and just very easily plot by going, 3 in this direction and then 5 in this direction, instead of going like 3.2 and I don't know, whatever the other number might have been. I'm going to just make this up on the spot. Do you have to have an orthogonal basis? Not necessarily, but we're not going to get into all that crazy 300 level. We call it linear algebra, but it seems a lot crazier than just regular old algebra. All right, so dot products. If it's 0, it's cool because it's orthogonal. It means those two vectors form a 90-degree angle and not necessarily just going straight up and straight right. They can be tilted. All right, so let's do a couple examples. Example 1, find the dot product. Then conclude if orthogonal. There we go. So for A, we're going to have 5i plus 7j. And for V, we'll have negative 2i minus 4j. The proof of orthogonality is not extremely difficult to do, but I think that when we demonstrate this with examples, it's going to be good enough to believe it. It's not like we're just pulling the quadratic formula out of thin air. So U is 5i plus 7j, V is negative 2i minus 4j. So the dot product, U dot V, we're just going to multiply the x components, which are 5 and negative 2. I'm supposed to be doing this in blue. Doesn't technically matter, but so 5 times the negative 2, and then we add. Now we multiply the y components, 7 times negative 4. 5 times negative 2 is negative 10. 7 times negative 4 is negative 28. So we can just write minus 28 instead of plus. And then adding those gives us negative 38. So that's the dot product. Because this is not 0, so not, I'm going to abbreviate this, orthogonal. Not the bug people ortho. That's it. That's the whole process. It's not some complicated process. It's kind of like doing a weighted average, the top of weighted average. If you're not familiar with that, then just ignore what I said. All right, for B, let's go with U equals 4i minus 6j. And let's go with V equals 6i plus 4j. Now, it's actually pretty easy to spot a pattern with orthogonal vectors if you do enough of these. I'm not going to spoil what the pattern is. I'd like you to use your own imagination to do that if you've done maybe several of these. But let's just do the dot product and see what comes out. U dot v. So multiply the x components, 4 times 6, plus multiply the y components, which is negative 6 times 4. Well, 4 times 6, each of those is 24, but one of them is negative. So guess what? Dot product is 0, which means since it is 0, it is orthogonal. Maybe you don't believe me. Well, if you don't believe me, draw them up. Let's do B. Let's actually draw it. I didn't ask you to, but it's just kind of proof of concept. I could do better than that. Better. So let's go about 6 in each direction. 1, 2, 3, 4, 5, 6, as neatly and evenly spaced as possible, because the less neat and evenly spaced we are, the more our point might not be driven. And then 1, 2, 3, 4, 5, 6. 1, that's a little far. 1, 2, 3, 4, 5, negative 6. All right, so I'll do u in blue, 4i minus 6j, so that's right 4 down 6. So here's the terminal point of that vector, right 4 down 6. So there is the vector u. V I'll do in red, which was 6i plus 4j. So we're going to go right 6 and up 4, which is about here for the terminal point. And look at that. I think that's a pretty good depiction of a 90-degree angle. I can't prove that with the picture. Now, again, the proof is quite simple. I want to leave this to you to try and kind of imagine where this would come from, or you can look it up on your own. But I just want to say that the general proof relates to the slopes of perpendicular lines being m for the first one and negative 1 over m for the second one. They're negative reciprocals of each other. So the x and the y components give you a rise over run. So for this one, the rise over the run would be negative 6/4. This one would be 4 over 6, which are negative reciprocals of each other. So if these two things are negative reciprocals, then they're orthogonal. They form right angles. But it just so happens to be that that dot product arrangement of all those numbers involved, it just means if you multiply the x's, add, multiply the y's, if that's 0, that's the same math behind the slopes being equivalent. So again, I've really pushed you in the right direction of the proof of that one. I just don't want to completely spoil it on my own in my teachings. But hold on, I thought it was in the book. I actually don't see it in the book. Yeah, they do their proof in a completely different way, actually. But if you look on page 808, you'll get a proof of it. And they just do it based on the cosine of an angle, based on a formula we're about to get, which we haven't seen yet. Okay, so dot product, pretty easy to do when you're given the components. Notice what I just said. A dot product is pretty easy to do when you're given the components. Well, guess what I'm about to do? I'm about to not give you the components. Instead, we give you the angle and the magnitudes. And when I say angle, I mean the angle between them. So here's the alternate form of a dot product. Say you're given the lengths of the vectors. So the lengths would be the magnitude of u and the magnitude of v. Also, not necessarily plus, I'm not saying plus, minus, I'm just saying also, you're given the angle between them, which we'll call theta. Now, I'm not saying the angle formed from the positive x-axis to the vector, I'm saying the angle between them. See, here's the vector u maybe, and here's the vector v. I'm saying we know the angle between them. Maybe here's your vector u, and maybe here is your vector v. I'm just making a different example. Theta is not the vector from u to the x-axis. It's not that. Theta is not the angle from v to the x-axis. The theta here is the angle between them. It has nothing to do with the x-axis. Now, if I give you the angles for u and v, you can find the angle between them by subtracting them. That does relate to the x-axis, but it's just because it's a subtraction. That's all it is. So if given the lengths of the vectors and the angle between them, the dot product, definitely not going to show you this proof. The dot product is the magnitude of one vector times the magnitude of another vector times the cosine of the angle between them. Trust me, the proof of this will hurt your brain. It's on page 807 of your text. You've got a lot of little components, a lot of little algebra to take care of, squares of terms and things like that. But it does boil down to this. It would take us probably 25 minutes to explain that proof. It's not worth the time. So if I instead give you the magnitude and the angle between them, and I ask for a dot product, you got to use this formula. But admittedly, what we usually do with this formula is, it's for when we give you two vectors, maybe in component form, or maybe with their magnitudes, and you want to know what's the angle between them. So I give you this vector, I say this v is 3i minus 5j. I give you u, which is 2i plus 3j. And I want to know what's the angle formed between them. This is another thing that can be really important in physics, just having two vectors, two forces in different directions, and needing to know the angle between them. Well, these things have nothing to do with x and y axes. They're all in terms of their own kind of world. So what you do is you just take this formula with the dot product and you solve it for this angle. So you divide both sides by this, which is why these things end up in the bottom. That isolates the cosine of theta. And if you have cosine of theta isolated, then you just take an inverse cosine of both sides to solve for theta. So going from the top formula to the bottom formula is actually pretty easy. It's you divide by these things, and then you take an inverse cosine to get rid of that. And you'll be done. Okay, well, inverse cosine is only valid in quadrants 1 and 2, so you got to be careful, right? Actually, no. Because inverse cosine is only valid for angles up to 180 degrees, we're talking about an angle between two lines. When is that ever going to be bigger than 180 degrees? This is the worst it could be. If this is your u vector, and then this is your v vector, that's 180 degrees. If your v points down instead, then the angle you get is just here. It would be the angle between them still, just the smaller one. You might go, well, maybe I want the bigger one. Well, then do 360 minus it, and there you go. So the other case is if you're u, and I'm just doing this relative to an x-axis, that would still be theta, and it would still have to be, that's terribly written, it would still have to be less than 180 degrees. So this is kind of nice. This is very convenient that there's no quadrant issues with this inverse cosine. Inverse cosine has kind of been our friend for the most part. It saved our butts with the law of sines and cosine stuff because we couldn't have angles bigger than 180 degrees in a triangle. And here, when we're talking about the angle between two vectors, we're never even going to consider that angle being bigger than 180 because if one of the angles is bigger than 180, just say the angle between them is the other direction, the smaller one. All right. Example 2. Example 2. And we're just going to find the angle between the given vectors. And for A, we're going to do vector U. Let's go with negative 2i plus 3j. And for vector V, let's go with 4i minus 5j. So this formula, yeah, admittedly, it kind of sucks to memorize. I am another thing that I always do is take other formulas and memorize them and rearrange them, as you've kind of already picked up. Me, I hate when that happens. Me, I always memorize this formula and then algebraically solve for theta in the two steps I've already described to you. Divide both sides by the magnitudes and then inverse cosine it. This formula just doesn't seem as bad to memorize. So the dot product is the product of their magnitudes. I mean, I just feel like that seems like something easy to remember. And then a cosine of the angle between them. Why a cosine? Just trust me. So yes, there's blatant memorization no matter which of these things you choose to do. But this one, at least, it's easier to give you the dot product and the angle, whereas this one is a little more convoluted to get the angle. You take the cosine of both sides and then multiply the denominator. Yeah, it's the same two inverted steps. It's just how my brain worked. All right, so the angle between them. All I asked for was the angle between them. So the angle is, well, hold on. How can I do the angle? The formula says I need to know the magnitudes. This is the component form, this is the component form. So, Mr. Vector, you gave me a problem I can't even do. Wrong. You can. If I give you the components, you can find the magnitudes by Pythagorean. So first thing you got to do is find the magnitudes. So the magnitude of U is the square root of negative 2 squared plus 3 squared. That's 4 plus 9, which is 13. The magnitude of V is the square root of 4 squared plus 5 squared, which is 16 plus 25, which is 41. We're going to leave the decimal approximations until the very end, because if I put an approximation here, then I'm processing an approximation, and then we get error propagation. All right, so those are the numbers that are in the bottom. Okay, so now we're ready to go, right? Well, actually, no, we're not. We need the dot product. That's the top of this thing. So that's one more thing that we actually have to process. So second, find the dot product. Some people will just jam that all in the formula at once, and that's fine. So u dot v, excuse me, said dot twice. Multiply the x components, which is negative 2 times 4, plus multiply the y components, which is 3 times negative 5. That's negative 8 minus 15, which is negative 23. Okay, so our angle would be the inverse cosine of the dot product, which was the negative 23. Let me just pull back so you can see the formula. What the heck just happened? Dot product is in the top over then just multiplying the magnitude, square root of 13 times the square root of 41. Oh, we can't have square roots in the denominators, Mr. Beckner. Doesn't matter, we're putting it in a calculator. So we'll round this to the nearest tenth, per usual. Check your mode. We're in degrees, so it should spit out a degree. Inverse cosine, negative 23 divided by square root of 13 times the square root of 41, question mark, question mark, question mark. Is this going to be the right answer? And then close off the inverse cosine. Big question mark, big inflection in voice. Error in domain. Well, that seems kind of weird, doesn't it? Because literally every single one of these has an answer. There will always be an angle between two vectors, or it could be 0, but it would spit out 0, or it'd be a 180 and it would spit out 180. So if there's an error in the domain, something must be wrong. We're supposed to be dividing by, both these square roots need to be in the bottom, but our calculator, typing it this way, it does not think the square root of 41 is in the bottom because it's only dividing by the square root of 13. It thinks that square root of 41 is in the top. So that's actually not good. Why didn't that work? I need to go and, before I put that first square root, I need to open a parentheses. I'm doing this for a reason because people mess this up all the time. Then the square root of 13 and close it. Then the square root of 41 and close that. And close the inverse cosine square root. And what we get is 175 degrees, rounded to the nearest tenth. So these vectors are almost pointing completely opposite of each other. It's pretty close. They're only 5 degrees off. If you don't trust that, you can always draw them up and just see that your answer makes sense. What do we got? 5 in each direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We'll do u in blue. That's -2 and then 3. Left 2, up 3. So here is u. We'll do v in red. 4i minus 5j, 4, 5. And because of my poor artistic ability, because I was not very meticulous with this one, it looks like it's 180, but it's not. Oh, I also didn't go down 5. That'll do it. Come on, stop that. All right, if I do this, oh no, that's a classic rookie mistake I made. All right, erase instead. 4, 5. That looks a little better. So again, it looks like 180, but if you were really, really meticulous about it, you could see that this angle would be the smaller of the two sides, and that's where the 175 degrees would be. So if maybe we had a force pulling in this direction and this direction, because they're so far off of each other, if their magnitudes are close to each other, they practically cancel each other out. Think about two people pulling on a rope on opposite ends of it. But this actually says that one person is pulling from here, there's like a joint here, and then someone's pulling from this angle. And physically what happens is it causes this joint to move out until it's straight unless it's bolted down. But you get the idea. All right, if I insert a page, is this going to screw up? Yes, it is. Oh, dang it. I really don't want to have this on 2 pages. But if I hit enter, that happens. Well, that's always so frustrating when that happens. Okay, here's what I'll do. I'm going to write B here. I'll open another page, and then it's fine. It's fine. U equals -2i plus 3j. V equals 3i plus 2j. Come on, I hit that 3 times. So it was 2i and -3j, correct? -2i, 3j. Okay, that's the first one. -2i, 3j. -2i, j. And v was 3j plus 2i. So you got to find the magnitudes, which would be, for the first one, the square root of -2 squared plus 3 squared, which is still the square root of 13. That's 4 plus 9. The magnitude of v would be the square root of 3 squared plus 2 squared, which shouldn't be a surprise. It's the square root of 13. 9 plus 4, 13. The dot product. Multiply the x components, which is -2 times 3, plus multiply the y components, 3 times 2. That's -6 plus 6, which is 0, which means, while I didn't ask anything about it, they're orthogonal. If they're orthogonal, that means the angle between them should be 90 degrees. So knowing that, I could go ahead and state that answer if I wanted to. I can say theta is 90 degrees and I'm done. However, let's ultimately prove it with the new formula. Let's practice. So theta is inverse cosine. And then we do the dot product in the top, which was 0 divided by. And then in the bottom, we're going to do the magnitude, square root of 13 times the square root of 13, which is actually just 13. But it doesn't matter because that's the inverse cosine of 0. I don't even need a calculator for that. Where is the x component 0 at 90 degrees and 270, but inverse cosine doesn't pick up 270, so it's 90 degrees. If you wrote 270, it would technically be wrong. My math, I would count it wrong. It's something I would count it right on a test. Actually, I take that back. I'm going to take this back. Hold on, negative 2i. They might actually say it's 270. That's a weird kind of I don't want to say this. I don't want to say this. So if you drew up these vectors, negative 2i plus 3j, that's left 2, up 3. Here's your u. Then v is 3i plus 2j. So that's right 3 up 2. So there's the j, the v vector, excuse me. And we can see that that's 90 degrees. This right here would be 90 degrees, whereas the other angle out here would be 270. My math lab is supposed to take only the smallest ones. The real deal is that you take the smaller of the two angles between them. If for some reason, because I feel like a student brought this up to me last semester, or 2 semesters ago, but this was back in April and it's November, so I might be thinking of another issue. If you're on a test and the answer, if you think the answer is 90 degrees and my math lab comes back and tells you it's 270, for this specific problem, you let me know and I'll give you full credit. Because the way I was always taught is you consider the smaller of the two angles because that's just the way we like to think. But again, it's always, these are just kind of respective angles. If that's 90, the other's 270. If the first one's 100, then the other's got to be 260. You can just kind of keep going with that from there. All right. That will close out everything that we're
Obviously, ignore the November part and give me a couple minutes while I'm setting up the next clip. All right, so we have finished all of chapter 7, so that's 7.6 and 7.7, 7.6 being done a previous class, 7.7 we just finished, and I already mentioned that we would be temporarily skipping chapter 10. You can see me just kind of talking about that here, and that test 3 would actually be on chapter 7 and 11. Again, you can see that there. We'll come back to chapter 10 when we have more time after finishing chapter 11, but we're going to go ahead and get that started. Chapter 11 is all about something called sequences and series. It's going to have massive, massive implications when you get to Calc 2, where we're going to learn how to take functions and approximate them with other functions, with portions of functions, and that sounds really weird. I know. I don't want to dive too deep into it now. We'll save that for another day. Let's start by putting the first brick in the building of sequences and series by learning the notation and how they operate, and how most of the initial stuff is actually quite simple.
File. Now you're going to notice I'm not going to be typing and writing a lot of stuff for this. I'm actually going to just kind of use my windows to hide, again, in the interest of time. There's so much material I want to get through by the end of this course, and me writing tends to add probably 10 minutes to the class. So boom, there you go. So this will probably be how I do maybe all of chapter 11, maybe. And then I'll just use some windows to hide things when necessary, like as we go over examples. It won't be too bad. I think it'll be fun. I've done it before, just not for this course. So chapter 11 is on something we call sequences and series. 11.1, we're going to start out with sequences and summation notation. So summation, that root word in there is sum, and that's exactly what summation notation is all about. It's about adding up a whole bunch of things, but one thing at a time. Sequences. Now right here I have what an infinite sequence is. And quite often an infinite sequence is something, usually with a little letter like an N or an I or an X or whatever, N being the most popular letter, I'd say I being the second most popular letter. And very often they're inside of curly brackets, and I know people always have fun drawing curly brackets. For me, my left one always looks a lot better than my right one. But this is just a common notation for a sequence. It's a set of terms where the domain, the thing that you're plugging into it, is the positive integers. Positive integers being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc. No negatives, no zeros. I'm not saying we can't plug in 0. I'm not saying we can't plug in negatives in general, but it's just usually just the positive integers when we're talking about a sequence. When we talk about series, a lot of times, sorry about that, we use 0. Each term of the sequence is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, all the way up to some whatever a sub n. So a sub n is just a general term. It could be the second term, it could be the 30th term, it could be the 4th term, it could be the millionth term. So this is just a sequence of numbers by the time you actually get this thing done. It starts out, it looks like an equation or an expression at first, but you'll be plugging in the numbers 1, 2, 3, 4, 5, 6, 7. This is telling you what number you're plugging in. To do a sub 1, you're plugging in 1. To do a sub 3, you're plugging in 3. To do a sub a million, you're plugging in a million. So the little sub notation guy or girl is telling you what number you're plugging in. Now, I'm actually missing an extra ... because it's infinite, it goes on forever. A sub a million, a sub a billion, a sub a trillion, a sub quintillion, quartillion, sextillion, septillion, octillion, nontillion. And again, that little a sub n is just the general term. A sub n is the thing that you'll be given. You'll be given something like a sub n equals 5n plus 3. And they can be simple or they can be complicated. A finite sequence has a bounded domain, which would have been without the ... So it'll stop at the 17th term. It'll stop at the 40th term. It'll stop at the 11th term, or it'll stop at the 100th term, or the 52nd term, whatever. So that's just the difference between finite and infinite. Infinite means it goes forever. Finite means it stops at some point. Bounded means stops. And domain, we said, is the numbers for the subnotation, just our positive integers. All right, so what we're going to do is we're going to write the first 4 terms of the following sequence. And let me get my other little covers up so we don't see everything. Right, the first 4 terms of the sequence. See, this works pretty well, doesn't it? A sub n equals 4n minus 1. So 4n minus 1 is just like our old school equation. And by the way, we are completely out of trigonometry with this stuff. We are not doing trig in chapter 11. Chapter 10, There is arguably an inch of trigonometry in it, but it really isn't. So we are done with trig. This is just more advanced algebra. Right, the first four terms of the sequence a sub n equals 4n minus 1. So this is kind of like saying y equals 4x minus 1, and I'm asking you to plug in 1, 2, 3, and 4. That's all it is. It's a slightly new notation. We tend to use letters like n and I instead of x and y. And that's just to help us distinguish between, old school equations versus sequences. So to do a sub 1, that means we're just turning the n into a 1. Do not overthink this. Just make the n a 1. So the red is showing what I plugged in. Because I want a sub 1, I plugged in a 1. 4 times 1 minus 1. 4 times 1 is 4. 4 minus 1 is 3. And that's it. That is the first term of the sequence. Then we want the second term, which means we go back to the 4n minus 1 and we just plug in a 2 instead. So that would be 4 times 2 minus 1. 4 times 2 being 8, 8 minus 1 being 7. Next up, we want a sub 3, which again, you're going back to the 4n minus 1, just 4 times 3 minus 1 now. 4 times 3 is 12, 12 minus 1 is 11. I know what you're thinking right now. Why weren't we doing this at the beginning of the semester? Arguably, we could have been, but we have to make sure we get every single ounce of trigonometry done. It's the stuff in Chapter 10, like I said, that if we don't hit something, it's okay. Chapter 11, we need to get it all. Finally, a sub 4 means 4 times 4 minus 1, which is 16 minus 1, which is 15. And remember, if I end up going too fast at any point, there's always the replay on YouTube. Much better than an actual live class in that regard. So that's it. That's the first four terms of the sequence. The answers that we got, 3, 7, 11, and 15. But we usually like to write down them in an actual sequence. A sequence means boom, 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 boom. They're going in an order. A sequence can be so many different things in our world. Sequences are seen all over in nature as well. This could be a sequence that says what our salary has been, our dollar per hour every year. So in 2017, we made $3 an hour. In 2018, we made $7 an hour. In 2019, we made $11 an hour. In 2020, we make $15 an hour. 2021, we could do 5 times 4 minus the 1, and then you get another number, and you keep going. And then our salary starts looking amazing, and no one's getting real pay raises like that. But again, just trying to relate it to something. You can use sequences and series to talk about the arrangement of petals on flowers. All sorts of things in nature relating to that. But then I have this typed up afterwards. Handwritten. Could you guess the next two terms? So with a lot of sequences, when we start jotting down what the terms are, 3, 7, 11, 15, very often we can establish a pattern with it, and then instead of having to go and plug 5 in here, instead of going, oh, that didn't work. Instead of turning this into a 5, 4 times 5 is 20, 20 minus 1 is 19, what you might realize is, all right, going between 3 to 7, we went up 4. Going from 7 to 11, we went up 4. Going from 11 to 15, we went up 4. If we went up 4 every time here, doesn't it seem really likely that we're just going to keep going up 4 each time? Which means we could just take the next one, 15 plus 4 is 19. And then we could guess the next one, 19 plus 4 is 23. And I don't have to just guess the next two terms. It's probably going to go 27, 31, 35, 39, 43, 47, 51. It's pretty easy to establish the pattern with this one. Is it always easy to establish the pattern? Of course not. you will see some variability there. Hold on a second. All right, so let's do another one of these. So for B, our A sub n, and these don't have to be A's, it could be a B or an X. These two letters can be anything in the world. But what is important is that pretend, I can't do that now. That's the one thing I have to remember. I can't click the pen icon. Pretend like I'm actually circling. This n and this n are the same as this. So if you want to find A sub 2, that means these are turning into 2's. If I want to do A sub n, over here on the right side, I can't make these i's. That would disagree with it. It's like, you know, if you want to do an equation in x, you can't just throw a z in there all of a sudden. You've now got a completely different variable. Now this top, pretend like I'm highlighting the top right here, the -1 raised to the n. Shoot. Spoilers. And pretend like I've highlighted the top. This is what I like to call an alternator. And no, not like in your car, but the same idea, in fact. Alternators go back and forth. Not physically, but the electric current that they put out goes back and forth. This -1 to the n, because we're going to be plugging in positive whole numbers into this, 1, 2, 3, 4, 5, 6, 7, 8, this is just a negative raised to either an even or an odd number of times. Negatives raised to an even number of times are positives. Negatives raised an odd number of times are negatives. So that's why we call this an alternator. It creates what we call alternating sequences or alternating series. This is seen 10 quintillion billion trillion times all over the math courses you're going to be doing in the future, especially starting in Calc 2. All right, so there's our sequence. So let's do the terms. Let's actually see that take effect. But again, it's just going to make, if one term is positive, the next one's going to be negative, then positive, then negative, then positive, then negative. So A sub 1 means those n's are turning into 1's, as we can clearly see here. Just ignore if you see anything over in this lower left region. So -1 raised to the first power over 2 to the first power minus 1. And again, this top thing is just a negative to an even or an odd number of times, which means it's just positive or it's just negative. That's a negative raised to an odd number, which is a negative. 2 to the first is 2. And then you still have the -1 in the bottom. 2 minus 1 being +1 in the bottom. And then -1 divided by 1 being -1. So the first term of the sequence is -1. Let's see what the second term of the sequence is. So the second term of the sequence, we just turn the n's into 2's. See, I'm using the red for emphasis. -1 squared, that's a negative to an even number, which is a positive, and then 2 squared in the bottom is 4. Sorry if you heard me gulping water down. 4 minus 1 in the bottom is 3, so the answer is a third. That's it. These problems are only as crazy as the arithmetic dictates. There's no a smart trig class here. There's no inverse sines and cosines being in different quadrants. This is just back to old school algebra. A sub 3, turn the n's into 3's. So these two n's turn into 3's. Now we're back to a negative being raised an odd number of times, which is a negative. 2 cubed is 8, so that's -1 over 8 minus 1. 8 minus 1 being 7, so that's -1/7. And look at this, they go negative, positive, negative. A sub 4, go back to the original thing, the original equation denoting the sequence, and turn those n's into 4's. A negative raised an even number of times is a positive, so the top will be +1. 2 to the 4th is 16. And in the bottom, 16 minus 1 is 15. So we get 1/15. Now, again, the answers, you just need the numbers. You don't have to write a sub 1 equals a sub 2 equals a sub 3 equals a sub 4 equals a sub 5 equals, etc. You can just delineate them with commas in order, of course. So -1, then 1/3, then -1/7, then 1/15. That's really weird. Where did the -1 go? It's all right. I must have hit eraser on accident earlier or something. Now, in this one, if I said, could you predict the next two, it's tougher. It's not like it's just adding 4 each time. It's, well, first of all, they go negative, positive, negative, positive. So I can at least predict that the next one is going to be a negative and the next one is going to be a positive. That aspect is pretty easy to predict. But the bottom number, 3, 7, 15, just trying to look at this without any of the actual plugging and chugging. Well, this one went up by 4. Then this one went up by 8. What's the next one going to go up by? Now, maybe you think about, all right, well, this was really -1/1, so it went up by 2. In terms of the bottom number 2, then the bottom went up by 4, then by 8. So that person might figure out, oh, the next time the bottom goes up by 16, and the bottom will be 31. And the next time it would go up by 32, and then it would be, what is that, 63 for the bottom. The tops are always 1s, and then you just go positive, negative, positive, negative, positive, negative. So could you predict it? Yes, but it is tougher. It's not as blatantly obvious. That's what I'm trying to establish, that some patterns are easier to predict, some are tougher. But by the time you're in Calc 2, you do need to learn some of these tougher predictions. So pattern recognition becomes extremely important as you're moving forward in math classes. Oh, there's my -1. It was bumped down there for some weird freaking reason, as well as the fact of what I was about to call this an alternating sequence. Remember, I call that -1 an alternator, -1 to the n. It makes this go negative, positive, negative, positive, negative, positive, negative, positive, which is why we call it an alternating sequence. Those things move because I hit enter at the beginning. That's why they're there. Word is weird. Weird is a word. Word, word. All right. What happened there? Why did that get so jumbled? Oh no. Oh no. Good grief. Okay. I really didn't want to have to write this over. I can fix it though. Boom. There we go. All right, so we still need the stuff hiding. I'm wasting more time than I intended with this, but that's because of word being weird. That's okay. We shrug it off and we move on. So I'm not going to do a whole boatload of examples of just plugging in numbers and doing very, very basic arithmetic and very, very basic algebra. You get the point with those two examples. We need to move on. So that's our simplest type of sequence, where it's a sub n equals something like 5n plus 3, or -1 to the n over 5 raised to the n, or 7n squared plus 3n minus 2. They don't have to be fractions. They don't have to have those alternators. They don't have to be linear. They can be anything in the world. Well, that thing I was talking about earlier, how a lot of sequences pop up in nature, they pop up in this idea in a recursive relationship. Recursion or recursive. Not cursive as in that type of handwriting no one uses anymore, or some words that we shouldn't use in class. Recursive or recursion. This is where the next thing is based on the last thing, or the next thing is based on several previous things. That is the world. The world is based on what just happened and what happened before it and what happened before it. Everything in nature that grows is based off of what happened before it and what happened before it and what happened before it. So your recursive sequences look more like this. You'll have your little a sub n, but then it'll be equal to, we can have something here like a 5n plus 3, maybe, doesn't have to be there. But then there'll be something involving a previous term. So if n is the term you're looking for, n minus 1 is the last term. So like say you're looking for the fifth term, if n is 5, n minus 1 would be 4. If I'm looking for the 70th term, this would be your 70 right here, the n, and n minus 1 would be the 69th term. Now, it doesn't have to just be based off of that. There could be a plus an a sub n minus 2. There could be an a sub n minus 3. I won't really do that in this course. I won't go past n minus 2. But believe me, in mathematics, we are opening the floodgates to amazing fields of mathematics where we study change in the world using this idea of recursion. Something new is based on something old. And this goes to something as simple as finding the interest in a bank account. Your new balance is your old balance times your interest rate. That's recursive. If you want to find your balance 7 years from now, you can find that based on the balance from years 6, 5, 4, 3, 2, and 1. Because year 6 is based on year 5 is based on year 4, but you would only really need to talk about the 6th one to find the 7th one, because again, new equals old times your interest rate. On a basic scale there. Okay. So for example 2, we're going to find the 2nd through 5th terms if the first term is 2, and the nth term, the general term, this is the formula to find any term, is 3 times the previous term and then a plus 1. So again, what this kind of says is the new term is 3 times the old term plus 1. Again, this really says the new term, a sub n, is 3 times the old term, a sub n minus 1, but then add 1 more. Now notice something. I told you what the first term is. I didn't ask you for the first through the 5th terms. I want you to pretend like this a sub 1 isn't here. Pretend like I just scribbled it out, but if I scribble it out, I'm going to screw things up. So pretend like that's not there. It's not there. There we go. If I just give you this and I ask you to find the first term, all right, the first term would be 3 times the 0th term, a sub 0 plus 1. Now I said usually we start with the positives, but I did say we can make exceptions and use 0. For series, we generally do. But hold on, what's the 0th term? Oh, Mr. Beckner, it's 0. If it's the 0th term, it's 0. No, it's not. The 0th term can be anything. So if I don't tell you what the old value is, you can't tell me what the new value is, because while there is a strengthened formula here, this 3 times and then add a 1, you can't figure out the new without the old. I'm not just plugging in here. That was what we did in the previous 2 examples. We literally just plugged in the 2 or the 3 or the 4, but this is not just plugging in the 2 or the 3 or the 4, this is plugging in the previous term in the sequence. So that's the thing about recursive problems, is that you have to be told at least one term as well as the formula between them. So the first term is 2, the nth term is 3 times the last term plus 1. So if we want to find the second term, sorry if you see some stuff up here, just ignore that. Focus your eyes where my mouse is. The second term would be, all right, 3 times. Now if we're trying to find the second term, that means the n is 2, so that's 3 times the first term. You'll see that in the next line. I'm just showing all my work meticulously here. So the second term would be 3 times a sub 2 minus 1, and then a plus 1. That plus 1 is not part of the 2 minus 1. That's completely different. 2 minus 1 being 1. So that's 3 times the first term plus 1. Again, all this says is the new term is 3 times the previous term plus 1. Well, I told you what A1, the previous term, is, 2. So this is 3 times 2 plus 1, which is 6 plus 1. That looks like a 7, but it is a 1. This right here looks like a 7, but it's a 1. This is a 1, just an ugly 1. I'm going to fix that. Ignore the things you're seeing. Ignore them. There we go. So the second term is 7. All right, well, how about the third term? The third term would be 3 times the previous term, and I'm going to stop doing the little 3 minus 1 bit here. If you need to show it, be my guest, but I'm not going to do it anymore. So the third term is 3 times the second term plus 1. So the new term is 3 times the old term plus 1. And again, these aren't always just based on the previous term. They could be based on 2 or 3 or 4 terms ago. They could be based on the previous term, the term before that, and the term before that. We're just keeping these a little simpler for introductions. All right, well, what's the second term? I wasn't told that at the beginning. You didn't tell me what the second term was. Well, no, but we did find it. It's right here. The second term was 7. A sub 2, blah, 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 is 7. So I'm going to replace this with a 7. So we get 3 times 7 plus 1. 3 times 7 being 21, and 21 plus 1 being 22. So that's the third term of the sequence. Let's find the fourth term. Which should be, again, 3 times the previous term plus 1. If we're at the fourth term, the previous is the third term. So 3 times the third term plus 1. Again, it's not 3 times 3 plus 1. We're not just plugging in 3. The 3 is being plugged into the subnotation. Well, I'm sorry, the 4 is being plugged into the subnotation. That's what gave us that 3 here. Again, plugging in 4 here, 4 minus 1 is 3. That's why that's a 3. What's the third term? You didn't tell me that. No, but you did figure it out. It's over here. It was 22. So that's 3 times 22 plus 1. 3 times 22 being 66, 66 plus 1 being 67. Trust me, I know this feels awful the first time you do it. Do 10 of them, you get used to it. It's a rule of thumb of life. Practice is everything. All right, fifth term, the last one I asked you to find. Now your homework, they'll ask you maybe to find the second through third terms, the second through seventh terms. You just have to pay attention and make sure you give them everything they want. So that'll be 3 times the previous term in minus 1 would be now a sub 4, then plus the 1 to the side. What was the fourth term? We just got it. It was 67. So 3 times 67 plus 1. 3 times 67 is going to be 201. 201 plus 1 is 202. I didn't write the 201 plus 1. But I said it at least. You can write it if you need. Now we have the second through the fifth terms. So if we wanted to, we can box them all together. Now maybe you wanted to write all 5 terms together, but I asked just for the second through fifth. That's why in the box I only have those. But I reminded us that over here that the first term we were given was 2. Now, what would happen if I changed the a sub 1? What if I changed a sub 1 to be a 5? How much does that affect these answers? Well, actually, quite a bit. Because now this, to find a sub 2, this would be 3 times 5 plus 1, which would be 15 plus 1, which is 16. That's significantly larger. That's 9 more. We went from 2 to 5, which was not a huge increase, just 3. But now we're already 9 bigger. Now the next one we'd be doing 3 times 16 plus 1, which is 48 plus 1, which is 49. Now we're 27 higher, and you can see that that would just continue on. So while the formula here does drive the pattern most of all, these values in size has a lot to do with how big or small your starting value is. So just making your starting value a little bigger, just a couple bigger, will make you hit the triple digits sooner, the 4 digits sooner, the 5 digits sooner. These numbers will blow up even quicker than how you see here. If I plug in a number like 50 here, holy cow, these numbers are going to be big just all of a sudden. Now again, trying to find a pattern here might be pretty tough. 7 versus 22, if you say, oh, well, that added, what did that add? All right, well, let's see. That's about 15. All right, then going from 22 to 67, oh, that's about 45. And then from 202 to 67, oh gosh, that's getting difficult. And when you're looking for pluses and minuses, or additions or subtractions, it's not always just as simple as that. So this is a pretty tough pattern to find. However, someone might be able to establish it that, okay, well, 7, and if you tripled that and then added 1, you'd get 22. If you triple 22 and add 1, you get 67. If you triple that and add 1, you get 202. But, well, guess what? That's exactly what this says. So you just keep tripling it and add 1, triple it, then add 1, triple, then add 1. So the next one, if you triple that, you get 606, add 1, 607. So this next one will be 607. Then you could triple that, which would be 1821. I'm sorry, 1822, because then you triple it, then you add the 1. And you just keep going. This right here actually is the exact pattern. When you look at these sequences, oh, this just added 4. I didn't see anything here that really said to add 4. But this thing is what said you just keep adding 4 because it was 4 times the n. That's what made it bump up by 4. The fact that there was an exponent in this thing in the bottom, that's what made me kind of realize that the bottom was increasing by 2, then 4, then 8, then 16, then 32. And again, I can't teach you how to see all these patterns just in 15 minutes. This is where you have to practice. You would want to do 50 of these, all sorts of different ones, just to get used to the pattern establishment. All right, got some spoilers on the screen, please ignore them. A sub 1 is 1, and A sub 2 is 2 times A sub n minus 1 plus 5. Now, if this was 2n plus 5, this would not be recursive. The next one would not be based on the previous one. Now, back in example 1, I used a pattern to find the next one based on the previous one. I said add 4, add 4, add 4. That was me establishing a recursive formula. I could just say that A sub n was A sub n minus 1 and plus 4. In other words, the new term is the old one plus 4. Let me show you what I'm talking about. This little plus 4 thing. I could rewrite this whole thing and say that A sub n is equal to A sub n minus 1 plus 4. And I can now have this as a recursive formula instead. So recursive formulas are much more about patterns already being established. All right. So this says, all right, to find the next one, double the previous one, then add 5. That's the pattern. But you can't just have the pattern, you have to have a starting point. So we tell you the first term is 1. Now again, this number will have a lot of strength as to what the answers are going to be. If I make this one a 2 or a 5 or a 10, these answers are going to get really big really quick. All right. So A sub 2. That'll be 2 times A sub 1 plus 5. So the second term is 2 times the first term plus 5. The new term is 2 times the previous term plus 5. That's what that says. Well, the first term we established was 1, so that's 2 times 1 plus 5. 2 times 1 is 2. 2 plus 5 is 7. Again, the difficulty of the algebra and the arithmetic here is just going to vary from problem to problem. All right, well, there's our second term. And I still want the second through the fifth term, same instructions as for A. So the third term is going to involve the second term. So that's 2 times the second term plus 5. The second term we just found, it was 7. So 2 times 7 plus 5, which is 14 plus 5, which is 19. For A sub 4, the fourth term will be based on the third term. If this was an A sub n minus 2, that would mean the fourth term was based on the second term. Again, real world, that happens. Other math classes, that happens. And here, we're just sticking to a simpler pattern. Fourth term is based on the third term, 2 times the third term plus 5. Third term being the last answer we got, which was 19. So that's 2 times 19 plus 5. 2 times 19 being 38. 38 plus 5 being 43. You know what can be a really good model to use with things like this? Population dynamics. Because the amount of people in 2021 is mostly based on the people that were in 2020. You know, there's deaths and there's births, but everything involved in 2021 is based on what happened in 2020. Predator-prey systems, if you want to model, say, I don't know, snakes and rabbits interacting together, you can do this type of thing. And it gets pretty complicated pretty quickly, but the basic idea is just that the number of rabbits this year is based on the number of rabbits last year and the number of snakes last year. But they commingle, they cohabitat. And it doesn't have to be rabbits and snakes. I'm just giving you an example of a predator snake and prey rabbit, unless you're in Monty Python and then rabbit's the predator, right? Ha ha ha. All right, ace of 5. Fifth term, last term we were asked for. So that will be 2 times the fourth term plus 5. Fourth term was the answer we just got of 43. So it's 2 times 43 plus 5. 2 times 43 is 86. 86 plus 5 is 91. I just didn't write the 86 plus 5. Make sure you pay attention in my math lab. Make sure that they only want the second, third, fourth, and fifth terms or whatever. So I can write to the side, yes, a sub 1 was 1, but if my math lab only asked me for terms 2, 3, 4, and 5, that's the 7, the 19, the 43, and the 91, the answers that we got. And it's annoying, but if my math lab only asks for second through fifth, if you put 1, 7, blah, 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 it's going to mark the whole thing wrong. It's another case of on a test, I would give you a solid amount of partial credit, if not full credit for that. Homework, you're just going to have to do it over. And again, test-wise, you'd have to email me and let me know. All right, how are we on time? 1:15, plenty of time. So again, I could literally do thousands of examples with this stuff. I could get it to become even more complicated, but we're going to stop there. I will give you an example of something being based off of 2 previous terms, something that I really hope you've heard of in your life at some point, and if not, here's a nice introduction to it, and it relates to all sorts of things in nature, like sunflowers, the Fibonacci sequence, which the traditional Fibonacci sequence goes 1, 1, 2, 3, 5, 8, 13, 21, et cetera, et cetera, et cetera. After that would be 34. After that would be 55. And then it just keeps going. It's a recursive formula. It's a recursive formula that says some term, so let's say this random term, oops, showing a little more than I want to. Let's get the highlighter. Let's say this term right here is found by taking these 2 terms, the 2 terms before it, and just adding them. That's all it is. Any term in the Fibonacci sequence you find by taking the previous 2 and adding them. So 21 right here, if I highlighted 21, 8 plus 13 gives us 21. So the 21 is based off of the previous 2 terms. That's how I knew the next one was going to be 34, because 13 plus 21 is 34. And then the next one will be 21 plus 34, which is 55. And then the next one would be, you just keep going. Now, what about this one? How do you find this one? How do you find the second term if it's based on 2 previous terms? Because it would be based on this one and a term that doesn't exist. Well, you can't. Fibonacci sequences, you can only establish terms starting at the 3rd one because they're based on 2 previous terms. I'll undo all my little circling and highlighting here. So this particular Fibonacci sequence, you have to be given the first 2 terms. And we're told they're 1 and 1. Notice I said that this is the traditional Fibonacci sequence. There are other Fibonacci sequences. All you do is change the first 2 terms. But the formula itself is always take the last 2 terms and add them. Fibonacci means take the last 2 terms and add them. The first and second terms are just determined by context. When we talk about sunflowers, when you look at the patterns of their arrangements and everything, some people can analyze them with the first 2 terms being 1 and 1. Sometimes you'll use a 1 and a 2. So there's like a second order Fibonacci, there's a third order Fibonacci, and you could just make up your own problem where the first one is 7 and the second term is, I don't know, 32. And then the third term would be 7 plus 32, which is 39. And then the next one would be 32 plus 39, et cetera, et cetera. So patterns of 5, 8, 13, 21 petals on things you can see all over the world. Fibonacci sequence in nature, just Google that and have fun studying that and looking at really cool pictures and patterns. Unfortunately, I don't have the time to teach that. We're not supposed to be teaching that in this course. I get to talk about it for a minute or two. I just don't get to show you all the bigger picture stuff, including literally the pictures. But man, Fibonacci is everywhere. All right. So this is what I was talking about, where I really don't do anything using a term from 2 ago, but you can. So this says that the new is equal to the one before it added to the one before that. Again, the sum of the 2 previous terms gets you your new term. So your 50th term would be the sum of the 48th and 49th terms. Your 101st term would be the sum of the 99th and 100th term. So Fibonacci is just a great example of using 2 different terms of a sequence, which means you can't be given just one starting value, you have to be given 2. Otherwise, it's impossible. All right. Next up, we have something called factorial notation, and this is only going to be for integers greater than or equal to 1. So we're not going to do 0, we're not going to do a half, we're not going to do -7/3. I'm not saying we can't. That's why I have an asterisk here. We are going to keep this under the simple construct of what factorial notation means, because it gives us a stopping point. Factorial just means if you want to do 7 factorial. This little exclamation mark, that's factorial notation. It's not saying in, it's not a super excited in, it's in factorial. That's how this would be read. This right here, you would read as in factorial. The word factorial has the root word factor in it. Factor means products. So that's why this is just a bunch of products. And look at this, it's this number you start with times 1 less than that, times 1 less than that, times 1 less than that, until you get to 3 and 2 and 1. So that's how you can tell where to stop. So in other words, 4 factorial would be 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. 100 factorial would be 100 times 99 times 98 times 97 times 96 times 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. These suckers get big fast, faster than anything you can imagine. Factorials, when you think about core functions like polynomials and radicals and rationals and exponentials, factorials are the quickest growing function that you've ever seen. And you go, well, Mr. Beckner, exponential functions, they grow pretty quickly. Factorials beat them. Because exponentials just mean you're multiplying the same number over and over and over. So like 5 to the 7th would be 5 times 5 times 5 times 5 times 5 times 5 times 5. So you just keep multiplying the same number over and over and over and over and over. A factorial means these numbers are getting bigger each time. So 6 factorial would be 6, 5, 4, 3, 2, 1. Oh, okay, well, some of those numbers are smaller than the 5, but now let's go to 10 factorial. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So the 10 through the 6 are bigger than the 5, which are going to have a bigger effect than the fact that the 4, 3, 2, and 1 are smaller. So that exponential equation might grow quicker at first, but the factorial is going to pass it eventually. It's kind of like if you have a motorcycle versus a car. Motorcycles have higher torque, which means they take off faster. But if the car's got higher top speed and they're traveling long enough, the car could eventually pass it and then win the race. So in this instance, exponentials are the motorcycle with this quicker acceleration, but factorials are the car with a higher top speed. All right. Now, I said 7 factorial would be 7, 6, 5, 4, 3, 2, 1. If you want to go in the other order, 1, 2, 3, 4, 5, 6, 7, nobody is going to care. Plenty of teachers do it that way. I just like to see the ending point last. super important, I say super important memo for, grand scheme of things, but we won't see it in this course. 0 factorial is 1, kind of in the same regard as anything raised to the 0 power is 1. Just take that at face value. There, we're not going to show a proof of that. It's nothing that we want to do in here. Just memorize it, but again, it won't be in this course at all. It's just something that might be in, say, Calc 2, and hopefully your Calc 2 teacher will remind you of that. All right, so let's undo my highlighting. Let's bring back my covers. And let's try this out. Let's actually do some of these evaluations. I've already talked about how it works, but let's see it. Sometimes just hearing it ain't good enough. So I know there's a word, a letter right here, kind of hovering the dot, but that's 5 exclamation marks. So it's not 5, it's 5 factorial. Sorry if I'm yelling in your ear. Sorry for my headphone people. I feel even sorrier for you when I cough. All right, so 5 factorial is just start with 5 and work your way down. Times 4, times 3, times 2, times 1. But Mr. Beckner, I don't really need to write the times 1 because times 1 does nothing. Okay, yeah, that's true. Sure, you could just write 5 times 4 times 3 times 2, and you will get the same answer. But this is just a little more explicit. It's being more specific, is what I mean by explicit. So 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120, and then 120 times 1 is, of course, just 120. I'm not pulling out a calculator for that quite yet. All right, that was easy. 7 factorial. I literally said this one earlier. I think I even said 5 factorial, not the answers, but just what they look like. You're actually going to have most of this last problem in it. In fact, you'll have all of the last problem in it. It's just going to throw a couple extra numbers in it. So you start with 7, then 6, then 5, then 4, then 3, then 2, and then 1. So 7 times 6 is 42. 42 times 5 is 210. 210 times 4 is going to be 840. 840 times 3 is 24, then another 2520. And then times 2 would be 5040. Times 1, of course, is still 5040. Now, that's getting to the point where you're probably like, oh, come on, Mr. Beckner. I'm pulling out my calculator for that. The 42 got annoying. You don't believe me? 7 times 6 times 5 times 4 times 3 times 2 times 1, 5040. Remember I said these things grow fast? Look at these two answers. 5 versus 7. We went from plugging in 5 to plugging in 7, and the answer went from 100 to 5,000. We're already halfway to 10,000. What if I did 8? Now you want to see something else cool? I already knew what 5 factorial is, so did I really have to type 7, 6, 5, 4, 3, 2, 1? No, I could have just done 7 times 6 times, now the 5, 4, 3, 2, and 1, if I just isolate that bit, that is 5 factorial. I'm going to annotate on the screen for a second. The 7 factorial, which was 7, 6, 5, 4, 3, 2, 1, since I already knew what 5 factorial was, this bit right here is 5 factorial. So I can just say this is 7 times 5 factorial. Now you cannot multiply the 7 and 5 and call this 35 factorial. I think very obviously that is obviously not right. 35 factorial would be some ridiculously large number. 35 times 34 times 33 times 32 times 31. So order of operations is critical. This factorial is kind of like a parentheses around it. No one ever writes that parentheses. All right, so 5 factorial is 120. So if I just do 7 times 6 times 120, I should get 5040. And sure enough, I do. So you can actually take previous factorials to find a bigger one. If I needed 10 factorial, I could just say that's 10 times 9 times 8 times 5040, because the 7 through the 1 would be 5040. And you can see that that would be a ridiculously large answer. And oh, I did write all that stuff here. I forgot that I had something there. I didn't have to do that little side annotation stuff. Is this being a pain right now? So again, these things grow ridiculously fast. And I left some crossing out, so I'm going to need to undo that. I want you all to close your eyes for 10 seconds. Please close your eyes. Please close your eyes. Let's see if I can fix this in 10 seconds. Eraser, please. Boom. Oop, too much. Again, keep your eyes closed. I'm not doing anything. All right, now you can open your eyes. None of you closed your eyes, did you? I wouldn't have. All right, so let's do something a little different. 40 factorial over 38 factorial. So 40 factorial is 40 times 39 times 38 times 37 times 36 times 35 times 34 times 33 times 32 times 31, 30, 29, 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. No, I did not go to school in the Valley. Let's do this. There we go. Perfect. I did not write all that, did I? I did not write all that because that would have been ridiculous. I even wrote more than, if I was doing this on my own, I wrote more than what I would have done. I would have just done the 40, the 39, then this little dot, 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 3, 2, 1. This is, the dot, dot, dot is showing 35, 34, 33, 32, all the way down to 10, 9, 8, 7, 6, 5, 4, and then you have the 3, 2, and 1. So you could go in your calculator and do that tedious monster of a problem, which is not what I'm going to do. How about the bottom, 38 factorial? Well, that's 38 times 37 times 36 times 35 times 34 times 33, 32. I'm not going to say it all again. Da 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 da, and then 3, 2, and 1. Do you really have to show the 3, 2, and 1? Some people will say no. Some people will just go dot 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 dot. It's up to you how well practiced and what method you like to do. So why have I done it like this? Why did I expand it? Well, if you didn't have your eyes closed like I asked, here's what happens. You have lots of pairs that are matching. 40 doesn't match, the 39 doesn't match, but 38, what's going on? 38, there's one in the top and bottom, so they cancel each other out. 37, top and bottom, they cancel each other out. 36, top and bottom, they cancel each other out. Now, I have the 35 in the bottom written, but not in the top. Don't let that mess you up and think the 35 doesn't cancel. This dot, dot, dot holds 35, 34, 33, all the way down to 4. So I'm canceling it somewhere in there with this 35. Then the 34s cancel, the 33s cancel, the 30s cancel, the 25s, the 22s, the 19s, the 17s, the 11s, the 10s, the 9s, 8s, the 7s, the 6s, the 5s, the 4s. I can see the 3s, the 2s, and the 1s cancel again, but everything in that dot, dot, dot canceled with everything in that dot, dot, dot. Meaning the only thing we were left over with was the 40 and the 39. And then it turns out 40 times 39 is 1560. If you don't trust me, calculator. 40 times 39. You gotta actually type the 4, please. 1560. A lot of people probably would have thought this problem is just a nightmare or just a ridiculously big answer because it involves 40 factorial and 38 factorial. And yeah, the top is a ridiculously big number. The bottom is a ridiculously big number, but the point is, and this is seen over and 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 over in advanced mathematics, tons of cancellation happen, which brings us down to something quite simple. Probability theory, if you want to talk about probability involving cards, you see a lot of factorials involving that stuff. So if you're much for gambling and cards, this math might help you one day. I'm not going to teach you how to gamble, but all right. At this point, I want to show you that your calculator does actually have this symbol in here. Now, I can only show you on a TI-83. Any other calculator, you're going to have to find it, but I can at least explain how to find it. If you have a button on your calculator somewhere that says PRB, which stands for probability, and I just tie them together, that's where you'll find your factorial. Now, there's no PRB on my faceplate. It's under math. So I hit math, and out of these main menus, PRB, so I scroll to the right to get there. And option 4 is our exclamation mark. Now, I can't just hit an exclamation and then a number. That's going to give me the answer as a factorial, which is not what I want to do. I need to type the number first. So 5 For me, I hit math, go over to probability, and then the factorial. 120. How about 7 factorial? 7. Go over to where that option is. You can type 4 or just scroll down to it. 50, 40. How about the 40 factorial divided by 38 factorial? Let's see if you tried to do it individually. What exactly is 40 factorial if you had simplified that number before reducing? Good grief. Charlie Brown is screaming right now, good grief. 8 times 10 to the 47th. Now, you can't even see all the digits. It's only going to display 10 or 11 digits. So you got to move that decimal right 47 times and you can't even see these numbers. Your calculator is incapable of displaying that number. It has the number accurately in its memory, but it's not capable of displaying anything more than 10 digits. Now, if you go to an online calculator, maybe you can get all 47 of those digits, 48 actually, because of the 8. But good grief, so you can't even answer what that is. Same with the 38 factorial. It's just a ridiculously big number, but this one's 10 to the 44, so its decimal only moves right 44 times. But then you divide them, do 40 factorial, divided by 38 factorial. You get the same answer of 1560. So now what you're thinking is, well, Mr. Beckner, you said test 3, I'm allowed calculators. Why am I going to do any of this work by hand? Why would you ever do that work by hand? I actually want to skip to E. No, you know what? I'll address that point after. I don't want to skip it because of the covering and everything. But why would you ever want to do this stuff by hand will be addressed 2 problems from now. For now, though, and I don't know why, but I have a song with Fernando in the lyrics in my head now, just the way I said for now. So, Fernando. What if we had 3 factorials littered all over the place in a fraction? Like so, 10 factorial, 5 factorial, 9 factorial. Oh, Mr. Beckner, you just showed me I can use my calculator. Yes, you can for this one, but you need to learn to do this stuff by hand because you can't always use your calculator. I'm going to show you a problem that your calculator can't handle. Most calculators can't handle. There are some that can. I hope you don't have one. So the 10 factorial, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 5 factorial, 5, 4, 3, 2, 1. 9 factorial, 9, 8, 7, 5, 4, 3, 2, 1. I skipped 6, but you get the idea. Notice I'm only going to expand the largest in the top and the bottom, though. So I expanded the 10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I expanded the 9, 9, 8, 7, 6, 5, 4, 3, 2, 1. But I didn't expand the 5 factorial, and there's a reason for that. The 2 largest ones are where you're going to see all that cancellation. This idea works in theory, but it's so easy to mess up. Again, pretend like I didn't have those canceled initially. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 9, 8, 7, 6, 5, 4, 3, 2, 1 with no lines through them. But the 5 factorial I put in red just to emphasize that I didn't expand it. Now, I didn't expand the smallest one because the biggest 2 will end up doing the majority of the cancellation. You'll lose the 9s, you'll lose the 8s, you'll lose the 7s, you'll lose the 6s. I didn't write them, but you lose them. The 5s, the 4s, 3s, the 2s, the 1s. So from the 10 factorial and the 9 factorial, the only number you're left with is 10, but then it's also being multiplied by the 5 factorial. Now again, do not do 10 times 5 and call this 50 factorial. That is a drastically different answer. 50 factorial, we already saw 40 factorial was 10 to the 47th. 50 factorial would be even bigger, like 10 to the, I don't know, 60th maybe. But no, this is just 5 times 4 times 3 times 2 times 1, and then multiplied by 10. Well, the 5 factorial we already know is 120. I can just borrow that from right here. So it's 10 times 120, which is 1200. Could you have expanded the 5 factorial? Yes, but you wouldn't see it cancel anything because the bottom is canceled completely. The bottom doesn't always cancel completely. They don't have to be whole numbers for answers. But the point is, when you've got multiples in a top or bottom, just expand the largest pair. top and bottom. Now, if there was another one in the bottom, if there was, say, a 6 factorial right here, then I could expand the 5 factorial and the 6 factorial because the 5 factorial would now have something to cancel a bunch of stuff with. All right, now let's get to the problem I said your calculator can't handle. And if you think, well, what about D? Well, let's try D in the calculator. So 10 factorial. I know it's annoying to get to it every time, but it's better than having to do it, right? Times 5 factorial divided by 9 factorial. Now, if the bottom had a second factorial, I would need to wrap it in parentheses to make sure that all of them were counted as being in the denominator. But there's only one in the bottom, so I can just go 9 factorial. 1200, same answer. All right, Mr. Beckner, you're annoying me with this physical handwriting expanding and everything. I'm just going to let my calculator do all the thinking for me. So I'm going to do 80 divided by 79. 80 factorial divided by 79 factorial. I've already spoiled what's going to happen. So 80 factorial divided by 79 factorial. TI-83 got this. Oh, no it don't. No it doesn't. Error overflow. Overflow means that you have a number in here that is too big for the calculator to handle. Yes, there are numbers that are too big for calculators to handle. Every calculator has a maximum number in it. The fancier the calculator, the bigger that number is, but we've hit the point of no return on this calculator. So 80 factorial and 79 factorial, both of those are too big for the calculator to handle. And the calculator, what it does is it does the factorials, then it does the division. So it prioritizes its order of operations. It says to do the factorial before the division. And as soon as it tries to do 80 factorial, even if I just do that on its own, 80 factorial is too big, so it shuts off and it says, no, go away, I don't like you. So you are stuck with this expansion idea. I'll even show you exactly what the largest one you can do is. Let's go to 68 factorial. It's close. Look how ridiculously large this number is. 2.4, 2.5 if you round, times 10 to the 96. That decimal is moving right 96 times. I have no freaking clue what you would call that in millions, billions, trillions, quintillions, septillions, nontillions. It's a big freaking number. You would not want to write that by hand. You would not get a question on a test that asks you what 68 factorial is, because it would involve scientific notation. But I can do this thing where I ask you to divide two really large ones. And all right, so let's see if we can do 69 factorial. Can the calculator handle that one? It can, because it's times 10 to the 98th. Now, you might be able to guess what this next one is going to be. That went up by 2. So this is probably times 10 to the 100th. I hit math and it didn't go. 70 factorial, drum roll, overflow. So this is some number times 10 to the 100th. So our calculator can only handle times 10 to the 99. As soon as it hits times 10 to the 100, it goes, nope, that's too smart for me. So we are about to do something that is smarter than a calculator. Can't say that too often. All right, so the 80 factorial, again, pretend like I didn't have those slashes here initially. I'm going to erase them. Your eyes are closed. Your eyes are closed. Come on. There we go. I have to be like a surgeon with the eraser. All right, so 80 factorial is 80, 79, 78, 77, da 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 da, 32, 1. 79 factorial is 79, 78, 77, 76, 75, da 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 da, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Guess what? Your 79s are gone, your 78s are gone, your 77. I don't have a 77 written in the top, but with the dot, 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 it's in there, it's gone. Your 50s are gone, your 40s are gone, your 30s are gone, your 20s are gone, your 10s are gone, your 9s, 8s, 7s, 6, 5, 4s, your 3s, your 2s, your 1s are all gone. Only number you're left with is 80. The answer is 80. that is such a simple thing to do by hand, but because a calculator is programmed to only think one way, it can't handle it. We can think different ways. We can approach problems from different angles. And that's exactly what we've done here. We have essentially circumvented an order of operations by reducing. Because multiplication and division are part of the same process. You just do them as seen from left to right, but if it's one big fraction, it's all one big step. This is one of my favorite problems to introduce as something that you can do and a calculator can't in terms of number crunching, because your calculator isn't smart enough to approach from a second angle. What time do we got? 1:40. We don't have enough time to do this next example, so I'll put it on the screen with a little bit hidden, just so you see what we're going to be doing next time. We'll start with example 4 next time, where we're going to write the first 3 terms of a sequence that has a factorial in it. So there's a reason we introduced the factorial notation, because there are tons and tons and tons of sequences with that factorial in it. So this thing has not only has a factorial, but it also has an alternator. It doesn't have a carburetor or an engine, just an alternator. And since I have 2 minutes to talk, I want to explain what this stuff relates to. I keep mentioning this all kind of ties in with Calc 2. Calc 1, you start establishing the study of change. In Calc 2, what we start eventually learning is how to take a function like x squared and turn it into a series of a bunch of different terms from a sequence, like -1 raised to the n over n plus 1 factorial. So we learn how to take things like a sine of x or a cosine of x and turn it into this something like a -1 raised to the n over n plus 1 factorial. There are ways to turn like an x squared, that was wacky, an x squared into something like 1 plus x over 2 minus x squared over 3 plus that. And I'm not saying what that one is. I'm just saying that you can take a single term function and approximate it with infinitely many terms of a sequence. And things like sine and cosine end up having a lot of these familiar, this alternator thing, this factorial thing involved in getting there. And then in calculus, you say, oh, okay, well, a function is this infinite series of terms being added, but I just want to approximate it using 2 or 3 or 4. And that's kind of what calculators and graphing technology is doing in some instances, is that we take something like a trig function like sine or cosine, where we don't really know how to actually evaluate them without just going to a table or using technology. But we could say that sine of x is approximately x, or x plus x to the third over 6, I think, minus, and I think I might have said a plus or minus opposite there, but it doesn't matter. But just the fact that you can turn it into a polynomial, where polynomials we do know how to evaluate. We can find the answers just with a plug this in and get it. Whereas a sine, you need your calculator or an archaic table. So we learn how to turn these functions that are not polynomials into a sum of a bunch of polynomials. And we talk about how if you just want to use 2 or 3 or 4 terms, how it's only accurate in a certain window. And man, oh man, is it a fun but complicated study.
And on that note, we will call it a day. So like I said, we did knock out 7.7 and 11.1. So when we come back for week 9, we'll kick off with 11.2. We'll talk a little bit more about test 3. We'll talk a teeny bit about the final. You know the usual drill on how things go at this point, I hope. But besides that, per usual, if you have any questions, please email me. And yeah, take care, everybody.